This is 3.1 Scatterplots and Correlation. So we want to type the following data into our calculator and make a scatter plot by hand of the data. So the data is SEC 2011, average points per game, and number of wins for each team. So make sure you type it in. If we put it in the 84, it's two lists because there's an X and a Y. And if you're using the Inspire, same thing, and make sure you label them on the Inspire. So if we make our scatter plot, we have to have numbers on our axes that are continuous or that are constant scale. Label them, so points per game and wins. Label the graph, and then plotted our points. Which variable is the response variable? Wins, because that's on our y-axis. Which variable is the explanatory variable? Points per game. It could be either way, but if you think about it, the explanatory explains the response. Response is a cause and effect. It's the effect. And the points per game will tell you how many wins. Not the number of wins will tell you how many points per game you have. So more than likely, our explanatory variable is points per game, and our response variable is wins. Now we have a new SOX. S is shape still. The book calls it form, but it's the shape of our data. Is it linear, parabolic, curved, two groups of data, clustered? So this data is linear. It's in this line. Outliers, still outliers. Does not look like there's any outliers. They're all along the same pattern. Correlation. So instead of center, we have correlation, which actually tells us direction and strength. And we'll get more into correlation in a little bit. But direction is the slope. Well, the slope is positive because it's going up. We don't have to get any more specific than that. Strength, or the spread, how close are the points to each other and to a pattern? It's also measured by the linear correlation coefficient. But these are relatively close together, so it's a relatively strong correlation. So what we would say, the data is linear and no obvious outliers. It is a positive, somewhat strong correlation. And we'll have a number to clarify that how strong or weak a correlation is in a second. So linear correlation coefficient, R, lowercase r, measures the direction and strength of the linear relationship between two variables. And we're going to use our calculator to find this. If we look at a graph like this, the correlation is 0. There's no pattern. You can't see any lines here. Correlation to negative 0.3. Points are kind of scattered about, but you can see a pattern, and it is negative, so that's why it's negative 0.3. Correlation of r equals 0.5. Points still kind of spread out, maybe a little bit closer than this one, but now it's positive, so it's a positive correlation coefficient. Here, points are a little bit closer together, still negative, so that's why it's negative 0.7. These points are even closer together, so 0.9, and it's positive because they're going up. And here, negative 0.99, and it's going down. They're very, very close to the line. So here's our formula. The sigma of x, all the x's minus the mean divided by standard deviation. Same for the y's, and then divided by n minus 1. That's like finding z-scores. It's kind of standardizing. We're trying to see how far away our points are from this line, or from each other, is what it's doing. Now, to find the linear correlation coefficient of data, we use our calculators. So on the 84, you typed them in your L1 and L2. Now what we have to do first, and you only have to do this once, is go to second 0, which will bring up the catalog, and you have the little alpha thing going, so you can hit a letter, and hit D, so we don't have to jump or keep scrolling through the whole thing. And we're going to go to diagnostic on. This will turn on some other things that we need. And then you only have to do that once. So now we go to stat and calc, and you want linear regression, ax plus b. Now there's another one, a plus bx. It's just where they put the y-intercept first, then the slope. It doesn't matter. They both do the same thing. So now we have our r value, 0.9358, or 0.9359 is what I rounded to. R squared we'll talk about in 3.2, as well as a and b. Right now we're just looking at r, the linear correlation coefficient. We look at the inspire. We put it in our spreadsheet, Control I, the new page, data and statistics. We don't actually have to do all this, but I guess we can show you how to do a scatter plot. Click to add variable. So points per game is what we put on this axis, and over here now click and put in wins. And there's our scatter plot. Doesn't start from 0, we could change that, but we don't need to. You can kind of scroll over the points and you can see the ordered pairs. Now, we didn't really need to go through all that. Hit Control I and just do a calculator page. So, menu, statistics, stat calculations, and linear regression. So, X list, I labeled it points per game, PPG, and wins. Everything else stays the same. Again, you have a whole bunch of stuff, and we'll talk about that later. R is 0.9359. And while we're talking about it, we'll come back to this to show how to do a scatter plot on here. Second, stat plot. Hit enter on plot 1. And then this first one, actually both these are scatter plots. This will connect it, this will not. And we don't really want to connect it. So we'll do that one. Our X list is the L1, our Y list is L2, and whatever symbol you want. I'm going to do little dots and hit graph. And then you can see it. And if you hit trace, you can go to all the ordered pairs. And that's all we need for right now. So if we go back to our notes, linear correlation of 0.9359, well, it's positive, and this is going up. And 0.9359 means it's very strong. So these points are pretty close together, relatively close together. And that's what it's talking about. Now, correlation facts. Correlation makes no distinction between explanatory and response. It doesn't matter which is which. To show you that, if we look at this data, or looked at our scatter plot, and we get our data, we have an R. Oops, I have to get rid of something. If we look at our R, 0.9359, I have points per game here, wins here. I can switch them. My scatter plot looks a little bit different. And this is still back in here. And my R value is the same. So if I switch it again, it's still the same. So changing it does not matter. R does not change when we change the units of the values for X and or Y. So if we put them from inches to centimeters, it's still going to be the same. R has no units, it's just a number. Correlation does not imply causation. Look at some of the ridiculous graphs that are here. U.S. spending on science, space, and technology, and suicides by hanging, strangulation, and suffocation. Look how close they are. Number of people who drowned by falling into a pool, and films Nicolas Cage appeared in. There's a pattern. Per capita cheese consumption, and people who died by becoming entangled in their bed sheets. Divorce rate, and consumption of margarine. So we have lots of things that look like they're correlated, does not mean that they cause one. We don't Just because we consume more mozzarella cheese does not mean that we're going to get more civil engineering doctorates, even though the graph says that. Correlation requires both variables are quantitative. You cannot have one qualitative. That wouldn't make sense. They have to be numbers, numerical measurements. Correlation only measures linear relationship, not curves. So if r equals 0, that means there is no linear relationship between the two variables. And a value of r close to 1 or negative 1 does not guarantee a linear relationship. We're going to look at a residual plot in 3.2. But if we look at this data, that looks pretty straight. It looks like it's linear. We can do a linear model. A pretty good line. They're pretty close to it. However, and we look here, we got an R value of 0.9789. That's pretty good. Except, if we were to do a different model, it fits perfectly. Because this is a polynomial, this is a curve, this is x squared. It is literally y equals x squared. That's exactly what it is, but it looked like it was linear. So you have to be careful when you're doing that. When we do a residual plot, again, we'll talk about that in 3.2. Correlation is not resistant, meaning it does change with outliers or extreme values. And again, we'll talk more about that in the next section. But let's see, if you look at this, we got an R value of 0.9359. I'm going to put in a value of 29.4 points per game and 1 win, which is obviously very different. Look what happens to the R value. Jumped all the way down to 0.7449. So it changes the line a lot. Again, look at it. The slope of the line changes. So it's not resistant. Extreme values do mess with it. And correlation is not a complete summary between the variables. We could give the mean and standard deviation of both x and y. So that's all that we need to look at when we're dealing with correlation.